Hi everyone, I hope you're doing well. This is lesson one of the third unit, and today we're going to introduce probability and talk about different types of probability. So math, this is a branch in math where anytime you are trying to attempt to predict what might happen in a situation, you're talking about probability. And if you assign some sort of numerical value to this, then you obviously have a situation like probability. And there's tons of examples, and we deal with this in our daily lives, even though we don't necessarily think about it. But the risk assessment, the chance of a drug working, given factors, things like that, the odds that something will arrive on time. There's just lots of situations where this happens. So if we assign a number, we can think about this as ranging from impossible to impossible. So the likelihood of events occurring can range from impossible, which would be the 0, to absolutely certain. And if that was the case, we would have 1, which is equivalent to 100%. So we often, when we're doing calculations, we deal with just these numbers from 0 to 1, so often decimals or fractions. But you could deal with percentages as well. So if I look at impossible, that's over here. If I look at 1 and everything in between, this would be like the same as 100%. And obviously this is 0%. And in the middle, you would have 50%. Something like that. And so there's a bunch of vocabulary we kind of need to we have in common that we all know. So let's just go through some of that stuff. So the first one here is outcomes. So outcomes are the possible things that can happen in a certain event. So for example, if we take something really simple like rolling a 6-sided die, we could say, let's say it's event A, and we'll use set notation like we did previously with Venn diagrams. All of those possible outcomes, you could list them, right? You get 1, 2, 3, all the way to 6. Those would be those outcomes that we would need to be aware of. And you could even say, right, the number of A, the number of outcomes then is 6. The specific outcomes are 1 through 6, but the number of outcomes is just 6 outcomes. And within this, we have what's called an event, or the desired outcome. And so that's kind of like a subset of all of the outcomes within a situation. So if we stick with that 6-sided die, for example, if I say what's the probability of rolling a 3 on the die, then I would write this as the probability of a 3, and I would use this notation of P for probability. And obviously I would just simply take the number of ways that 3 can happen, which is really easy in this situation because there's just one way it can happen. And I'm going to take it out of the total number of all my possible outcomes, which is 6 in this situation. And so that's an example of what's called theoretical probability, because I can actually just look at the number of outcomes and just count them and figure it out. Sometimes you can't do that, and sometimes it's like if you were testing a drug or something like that, it's impossible to get the theoretical probability. And so sometimes you have what's called experimental probability, where you have to do things called trials. And a trial is just one experiment or one repetition of an experiment that you can then use to figure out probabilities. So associated with that is this idea of a sample space, which we've talked about with this S. And the S, remember, is the universal set. Sometimes it's really easy to find the universal set, like a 6-sided die. The universal set is just 6 different outcomes. Other times it's going to be a bit harder to figure out. And we've kind of seen that in different situations with permutations and combinations already. So if we were to estimate probability based on experiments, so you can base it on experiments, observations even. Anytime you're collecting data or those people in bio or ESS, you often can run simulations as well. So let's just talk a little bit about experimental probability. So if we're talking about experimental probability, it looks really similar to theoretical. But we've got the probability, which we said earlier, so this is P, of a certain event A. And then this represents the number of ways A can occur. And on the bottom, if I run that, and I'm running it through an experiment, then it's simply the number of trials that I divide by. And so the number of trials, if you do it 20 times, then that's going to be your number you put in the denominator. So pretty simple and straightforward. On the side here, not to go into it very long, but this was a survey done for people to assign a probability to certain expressions in English. So if I was to say, something was almost certainly going to happen, what number would you assign to it? And these are box and whisker plots. You've probably seen them in grade 9 math, which we'll talk about again later in this course. But somebody who, if I say something almost certainly, it looks like most people have said 90% or above assigned to that. So something associated with this idea of probability and also stats with that. We'll come back to that at some point. So we've got regular experimental probability. We have what's called theoretical probability or just probability. There's also a couple other things called subjective probability, and then we talked about this outcome. Let's just match these things up here with their definitions. So the first one is calculated based on the number of times the event occurred divided by the total number of trials. So that's just what we talked about. That's experimental probability. Second one, a possible result of an experiment. So that's outcome. The next one, percentage chance or decimal equivalent of something occurring. That's just probability or theoretical probability. And the last one, this one we're not going to talk a lot about, but it does exist. This is subjective probability, which is an estimate based on personal experience or intuition. So subjective probability really fits into situations where you can't necessarily run trials and you can't come up and just count the number of ways something can happen. So it would be based on what you think could happen. And sometimes that occurs in sports where people have opinions. Sometimes they'll use data to help them figure it out, but ultimately it is subjective in various instances like that. So let's take a couple examples with experimental probability. It says, suppose you flipped a coin 30 times and tails showed 19 times. The outcomes are H or heads and T for tails. And let's say the desired event A is tails. So I would write this like this, the probability of A, and then I would take the total number of ways it occurred, which in this case was 19, and divide by the total number of trials, which is 30. And I could technically just leave this like that, or I could represent it as a decimal. Either is fine. Let's just say we round it to 2 decimal places. I get approximately 63% or 0.63. So some people will go further and represent it as a percentage, but you don't necessarily need to unless you're asked to do that. In math, we always keep percents as decimals when we're going to be doing calculations with them, so it's often easiest just to leave it as a decimal or as a fraction. The second one here, it says Bob was frustrated with the length of time that the traffic lights were red near his house, so he sat around for an afternoon and surveyed their lengths. So he's collected this bunch of data, he's made observations. It's shown to the right in this table. It says, find a 2 decimal place of the experimental probability that the next traffic light will last the following. So part A says the probability then from 20 to 39 seconds. So 20 to 39. So if I go to the table let's just circle that here. So I got 20 to 39. And the frequency, which we know is the number of times something occurs, so it occurs 38 times. So that's going to be my numerator. What I need here is the total number of trials. So if I look at how many traffic lights he actually went and counted. So if I was to take all of these numbers in frequency and add them up, that gives me the total number of trials, which in this case is 78. So I'm going to divide by that total number of trials, 78. And again, I could leave it as a fraction, or if I convert this to a decimal, I get approximately 0.49. And if we go on to B, it says, well, what's the probability between 20 and 59 seconds? So I'll say 20 to 59. And I would obviously just take those numbers that we have represented with each interval, so 38, and then the next interval plus 19. So I'm increasing the chance that this is going to happen because I'm increasing the range of what those possible times are. So I end up with 57 over 78. And if I convert that, that's 0.73. Pretty straightforward. And so this is the only time we're really going to talk about subjective probability. So it says a subjective probability must always have a reason or justification for your answer. At least that's what this textbook is saying. You could just come up with things that you can argue or not argue, but we'll use this definition. So it says what type of probability is associated with the following? Give an explanation. So what's the probability that the next pair of shoes someone buys will be the same as the last pair they bought? So this would be an example of subjective because it's based on that person's experience. So it's based on personal experience or preference. The next one is what type of probability is this? Senators will win the Stanley Cup. Technically, like if you were to go to different websites that give you the odds of something happening, they're likely not to be the same. And so even though they all have the access to the same information, the same data, you're probably not going to find exactly the same numbers in terms of the likelihood of this happening, which because of that, this will make it subjective, right? How you interpret the data for this really does make it subjective. So I would say because we will interpret the data differently. So if I was to poll each of you and ask you this question, will they win the Stanley Cup? Maybe we're all going to just say no, but we're probably going to have different numbers to go with that chance, unless maybe they're all zero. But anyway, you get the idea, hopefully, that because we all have different opinions about it, that makes it subjective, and we probably assign different numbers. So part C, the next person to enter this classroom will be taller than 6 feet. I would say this could be experimental or subjective. You could argue this one. And it could be experimental, or maybe if we all had access to the same data, it's less, we could interpret it less about being subjective and just, how many people are over 6 feet. If there's no people over 6 feet, then maybe this is easy, that kind of thing. Okay, so I just want to illustrate a point about experimental probability in comparison to theoretical probability, which is what we're really going to focus on in this unit. So I would like you to go to this website, so you can go to the link, and it's just a simulator for tossing coins. And initially, so I'll go back here, what we're going to do is I want you to try to simulate tossing 10 times, and then we'll go to 50, 100, and 1,000. And we'll put on what's called the relative frequency in a second. So we're going to record the number of heads. So I'm going to change this here, so repetitions to 10, and I can leave the probability of getting tails or heads at 50, and I just press toss. And down below, it gives me my outcomes. So we got 3 heads. So I'm going to use that. I'll put that in here so you can put whatever you got. And then it asks for relative frequency. And relative frequency is just the frequency divided by n, which is the number of trials in this case. So I get 3 out of 10. And I'm going to convert this into a decimal because, we're going to compare these each time to each other. So this is nice and easy, so that's why I kind of picked these numbers. So 3 divided by 10 gives me 0.3. So let's go back and do it for 50 times. So I'll increase this. I can toss, and I get 26. So that's here, 26 heads. 26 out of 50, which gets me 0.52. Go back, let's go to 100. Again, you could try these, get different numbers. It's good if we were all there doing it. This one I get 47 heads, so I'll go back. So 0.47, and try one more, or 2 more rather. So I'm gonna now increase to 1,000. Toss these, and I get 521, and I'm going to do it twice, so 521, remember that, and then 464. So 521 out of 1,000, which gives me 0.521, and then 464, 464. So what I want you to see here, and we can't see it exactly the way I was hoping it would turn out, but that's okay. So what does the relative frequency become close to as you increase the number of tosses? So you can definitely see this going from a small number like 10, and each time I'm going, it's not obvious here, but if I was to increase the number of trials, what's happening is the number is getting closer and closer to 0.5. And so obviously in the first one, 3 out of 10 is way off of that. We got kind of lucky with the second one, 26 out of 50. If I was to do that again, I probably wouldn't get something so close to 0.5. But the idea is this is getting close to what is called the theoretical probability. And the theoretical probability of tossing a head. So like if you just said, well, what's the probability that you toss a head? Hopefully everyone's aware it's just 1 out of 2, which is 0.5. The idea is that if you increase the trials for an experiment, you're ultimately going to get closer to the theoretical probability. So if I was to do 10,000 trials, I'm going to be closer to my theoretical probability. And this is why we do experiments sometimes when you can't determine theoretical probability, because the idea is it's going to give you something that is close to it over time. And so how do these compare? Well, they're similar because, and this is the concept I want you to know, as we increase the number of trials, we get closer to the theoretical probability. And that will always be true. Okay, so hopefully someone is there covering this class. What I'd like you to do is, with a partner, it's going to sound like a lot, but it's not that much. I want you to use experimental probability to try to discover what the theoretical probabilities are for tossing 2 dice. So I'll explain this. You are going to roll 2 dice 100 times. And you're going to record the sum of two dice in this table below. There's lots of games that involve rolling two dice, and you take the sum of which. So for example, you could have a sum of 2. So that would be a 1 and a 1, all the way to the sum of 12. And some people might know the answer to this, but one of these sums is more likely than the rest. And there are probabilities we want to be able to figure out and understand. So you can keep a tally here. For example, if I get a sum of 4, I put it like this. If you get 5, you go like that. And then your frequency would be like this. And hopefully, if you do exactly 100 trials, then it makes these calculations easy, like this. And then we're going to compare what you get to your theoretical probability. So with a partner, we'll make this easier and quicker, but you can do this by yourself if you want. And so at the end, I want you to see which of your sums is most likely to occur, and we'll discuss that. And then which sum is least likely to occur. Okay, enjoy this. Try to keep those dice from flying around, and hopefully I will see you very shortly.